Howdy, y'all. Welcome. I am Professor Parks, PhD, and I do content on astronomy, science skepticism, and mental health. Today, instead of my usual shouting into the void kind of thing, I actually want to talk about a project that I just started doing because of help from supporters of this channel, which I am very grateful for. But before I start in on that, two things related to a channel supporter by the name of Eric E. He was kind enough to get me this. Sadly, I'm packing. I'm moving around my office because I get bored, and I seem to have misplaced my kettle, and so sadly, it is just vitamin water in here and not the precious bean juice that makes me go where I need to go. But yes, it does say, please do not confuse your Google search with my PhD degree, which I commented that I like this sort of thing, and Eric was very generous enough to order it for me. It was a surprise. I really liked it. The other thing is he's talking about, he has been DMing me, asking me about this thing called a Roche lobe. Now, for those of you who are not aware, a Roche lobe is essentially a gravitational equipotential surface where the gravitational force, for lack of a better term, is exactly equal to the centrifugal force. Basically, what that means is if you are sitting on the Roche lobe of a planet or anything with mass, and you are perturbed in any direction, you are free to move in that direction without constraint, in the sense that if you get touched, just given a slight amount of force outward away from the planet, you will move away from that planet without returning to it. Roche lobes are typically talked about in astronomy, or at least I'm familiar with them, in terms of formation of moons. If you have a small enough body, well, if you have a body of a certain size and it passes through the Roche lobe, then because of the added gravitational shearing that occurs to that satellite, it will get disrupted and basically break up into smaller chunks. The Shoemaker-Levy 9 comet is a great example of Shoemaker-Levy 9 is a great example of when an object passes through the Roche lobe of a major body, in this case, a comet passing through the Roche lobe of Jupiter, and gets shredded into, I think it was 12 cometlets. They went around and then came back and actually machine gunned the surface of Jupiter. And so, hey, welcome, Maya. Howdy. Georg, Stephanie, Mariaki. And so, yeah, we're talking about the Roche lobe. I think what he was talking about is, or what he's getting at is that it is I think you can use it to talk about the mass of the Earth, or the radius of getting the radius of the Earth. But actually, I was thinking about this in terms of what Stephanie seems to have a hurdle with, which is the Earth is moving 1,000 miles per hour at the equator. Why don't we all spin off on that? Well, when we think about it, with the Roche lobe, the way that the Roche lobe is defined is when the gravitational force and the centrifugal force, that force which would throw us off the surface of the body, is equal to 0. So if you were above that surface, the centrifugal force would send you flying. If you're below that surface, then you are gravitationally bound to the planet. And what we find is that the Roche lobe for the Earth is far above its surface. So when you look at the ratio of the centrifugal force, the force that is the spin force that is trying to throw us off our spinning Earth, and the gravitational force which is holding us to its surface, that ratio is exceedingly tiny. Oh, howdy, 42. That ratio is exceedingly tiny. And so gravity drastically overpowers the centrifugal force. But he was asking about this, and I have my handy dandy Solar System Dynamics by Murray and Stan Dermott. I was taught by Dermott, who is as English an Englishman as I have ever encountered. This is not even the first edition. This is actually a preprint of his book, Solar System Dynamics. I know the rest of you are going to find this incredibly useful or entertaining, but oh, sorry, Eric. All it tells me is that the value you're looking for of 2.46 radius of the planet is from Chandrasekhar 1987. Somewhere in here is references. Hey, like a good textbook, it actually gives me references. Chandrasekhar. Ellipsoidal Figures of Equilibrium. It's a book by Dover, New York. So S. Chandrasekhar, 1987, Ellipsoidal Figures of Equilibrium. Eric, if you watch that, that's the reference you want to look into. So, Chuck, anyway, that's not what I wanted to talk about today. What I wanted to talk about today is tangential related to it, and that is channel supporters. I love me and my channel supporters. They are awesome because they allowed me to buy this little beauty for myself, which I just looked up. Retails for $500. So, astronomically speaking, $500, that's kind of within people's budgets. If you save up and stuff. So it's not like, it's not like thousands of dollars. But what I have here is this little thing. Now, I really wanted to have this more prepared, but since I have been busier than a 10-dick dog in a fire hydrant factory, I haven't really had the time to actually set this up the way that I wanted to, and show you and have the images in a format that you can appreciate. Yeah, whatever. Howdy, Al. So we have this little this doesn't look like a telescope, and I know the lighting in here sucks, but essentially this portion right here, is the telescope itself, and it will rotate up and then rotate around to point at anything in the sky that you want to point it to. Now, with the proper filtration, such as this doohickey, this is a solar filter. So if you place this in front of the cap, if you cap this thing, filter it properly, then you can look at the sun, which I have done pretty much every day that I have had the chance to actually use it. So right now I'm going on, I think, day 4. Sorry, spilled stuff. Day 4. Let me see if I can bring up an image or 5. Let's see. The idea here, and I'm not just doing this for fun and profit. Well, the profit's nice. Fun's also nice. I'm doing this for a scientifically valid reason. So where we go? Let's go with that one. Yeah, that one's good. Let me do this. Yep, hold on. Bear with me. Tacking is hard. Let's do this. Let's present. Share screen. So that Is it an image of the sun? No, it is not a directed energy weapon. And actually, I'll talk about the EV Scope 2 that we just purchased here at the observatory through funds that I managed to acquire, not through patrons, but through, the university itself. That looks like a directed energy weapon. This is a picture of the sun as I took, I think it was a day or two ago, with this little guy, or gal, I don't want to misgender it. And you can see, even with this values, you got some sunspots going on right there. You got a monster sunspot over here. Now, what's nice is I have a collection of these going. Like I said, I have one on the put away everything. Hold on. I have an image on the 14th. I have an image on the 16th. I have an image yesterday, and I'm going to be going up and taking an image today. Now, the reason why I want to do this, and really I'm telling people this for a couple of different reasons, is somebody out there may be able to actually help me with this. Because with this $500 instrument, which I love, you can take images like this, which are fairly high resolution. Howdy, Clydewell. And what I'm hoping to be able to do with this is to have, in technical terms, a longitudinal study of the sun. In basic terms, I want as many images, as many continuous images, like once a day images of the sun over the course of a year. The reason why I want to do this is a couple of reasons. One, you can determine the angular size of the sun with these images and you can actually do it with, error bars. You can actually take a measurement of the sun rather than hand waving and saying it's half a degree or so. You can actually make a precision measurement of how big the sun is in your image if you know what your plate scale is, and I'll get into that in a second. But if you can determine the angular size of the sun to a well enough precision, then what I'm hoping to be able to demonstrate is real data that shows the relationship of the sun's size as a function of time over the course of a year. Because we live in a heliocentric world, because the Earth is orbiting around the sun, and not only because the Earth is orbiting around the sun, but because the Earth is orbiting around the sun in an elliptical way, the size of the sun is going to change as a function of time. In the winter, we are closer. In American winters, in the Northern Hemisphere winters, we are closer to the sun. In North American summers, we are farther away from the sun. It's a 3% change in distance. For the life of me, I can't seem to remember what the change in angular size for the sun would be, but it should be measurable. It definitely will be observable. And so that's what I'm hoping to be able to do, is to do that, present the data. Yes, same with Europe. Not only am I North American biased, I'm American biased. Or Northern Hemisphere biased, I'm American biased. So what I'm hoping to do with this is to be able to show with real data that I took with this instrument, which I would argue is within the budgets of most people, most first world nation people. Granted, I'm not belittling that. $500 is steep. That's a good chunk of change. You have to really, really want this, which I really, really did, in order to justify shelling that out. But in comparison to other instruments that you can buy to do this kind of work, this is actually on the cheaper side. So if you are interested in doing this kind of science yourself, if you have, if you are curious about what the size of the sun is and how the size of the sun changes, and you want to do this kind of thing, this kind of measurement yourself, it can be done. And I am want to be completely transparent about this. I've got the images. They are in PNG files. I think this is a PNG file, but the nice thing is that this has, and over on the GMU Observatory channel, which I hope you all subscribe to, the GMU Observatory channel, or George Mason Observatory YouTube channel, is solely about the observatory and what we do here. I, of course, run it now that I'm the interim director. And over there, what I'm going to do is either have a video or hopefully even a live stream where you'll have to call me Dr. Parks over there because, professionalism, all that kind of good shit. But over there, I will be talking about two different types of a similar type of scope. So this is the C-Star. The other one I've mentioned before is the EV Scope 2. And on that channel, I will basically do a compare and contrast of those two instruments. The EV Scope 2 is bigger, a bit more robust. The tripod is certainly larger, but it costs around $2,500, so 4 times as much. So I wanted to give people a really nitty-gritty kind of comparison about what to expect if you were to buy one of these scopes as opposed to an EV scope, because both of these telescopes are designed to do two things. One, provide a very easy entrance onto the superhighway of astrophotography. This is exceedingly easy to use. You have an app on your phone that controls everything. All it needs to know is its GPS location. It uses GPS to figure out where it's located in the sky. You've got to calibrate its internal compass. You got to level it, and that's it. That's all you need to do. It knows where everything is in the sky at that point, or at least it can find it on its own. EV Scope is the same. Very easy to use. It's a very cool tool to start if you're interested in. Yes, I am in fact why is my cursor's over here? Teching is hard. Yes, I am in fact now the interim director of the Freemason Observatory, where we do not hide aliens on a daily basis. And yes, download the approved NASA filter. But again, where did I put it? For this scope, this solar filter comes with. This is included. So this type of scope, the EV scope, they are designed to allow people to get into astrophotography basically immediately. You can take it out of the box with, I think, a very shallow learning curve, particularly for this scope. You can start taking really cool images of the night sky. I first trained it on the sun because, well, it was clear during the day and crappy at night. No, Rob can't mouse. And so I'm going to be very transparent with it. Where I was going with this is that with this particular scope, it's very easy to get the files in a particular file structure. I mentioned PNG. I hope everyone is probably familiar with PNG, JPEG. For astronomers, when we talk about astronomical data, we save images as FITS files, FIT or FITS, flexible something, something, something. Yeah, I know, I'm very technical about it. But it is a universal image file that all astronomical software uses. GIMP will recognize it. Photoshop recognizes it. So what I'm saying is I have these FITS files. If you are interested in if you cannot take the data yourself, PNGs need a container, yes. If you can't take this data yourself, you can't afford this or what have you, let me know, and I can give you the data that I'm collecting. That way you can do the analysis on your own, and you can compare to what I'm getting, because what I'm really hoping to be able to do is to show with fairly high precision what the sun, how the size of the sun changes over time. In addition to that, what you can do is you can also, or kind of this falls out of the process, is I talked about this thing called plate scale. All right, so we have this image of the sun right here, right there. Where's my cursor? So, all right, I guess you can't see it. Ah, there it is. I can mouse. See, C42, I can mouse. So you have the image of the sun here. Now, this image is composed of pixels, or little little pixel elements. And so what you can do is in GIMP or any other type of tool that you can get a hold of is you literally measure the distance, pixel distance, from the top of the sun to the bottom of the sun. Now, right now, I'm doing it by eye, which is not the most scientific way to do this. So the exact process that I'm doing this is evolving. But right now, I am just doing a by eye straight line measurement from top to bottom of the sun, and I get the pixels. So now I know what the sun size is on my image. Say it's right now, I'm finding it's about 812 pixels in height. Now, how do I change that? How do I get that into units that matter, such as degrees or arc minutes or arc seconds or even kilometers, something like that? Well, you need to know what you need to have a plate scale. Now, let me see if I can do this. The way that you get a plate scale is you take an image. Trying to do apples to apples. So here is an image I took last night of with this same scope of the Whirlpool galaxy. This is I think 5-minute exposure on a stacked image. So you have one little galaxy getting eaten by a big galaxy. But I'm actually not interested in the galaxies in this image. What I'm interested in are the stars. Now, the stars, as you might expect, have pixel positions all over this image. So if I define the upper left as 0, 0, then this might be, I don't know, 500 pixels X and 100 pixels down. It'll have a certain pixel position. But the star also has a position in the sky. It has a right ascension or declination, or in more layman's terms, a stellar longitude and a stellar latitude. So very much like cities have longitude and latitude coordinates, stars have coordinates of right ascension and declination. Effectively the same thing. So now I have pixel position, and I have the position in pixels. I have the position in RA and dec. I have those two things. Now, if I can do that for really you only need two. If I have that one and that one, what I can do is I can then say, all right, this is a certain distance, linear distance on the image of, say, 800 pixels. I can then do a little bit of spherical trig to figure out what is the angular separation between these two stars on the night sky, given its right ascension and declination, and for both stars. You can do this on the Earth. If you take the longitude and latitude of the Earth of two cities, you can do a little bit of spherical trig. I'm sure there's an online calculator for it. And you can figure out what is the angle across the Earth's surface that subtends those two cities, that separates those two cities. It's an angular thing. So now what I can do is I can use that angular distance between those two stars. I have a pixel distance. I now have a scale factor. I now know what is the angle? What is the angular measurement of 1 pixel? Right now, I'm finding that my my pixel scale is, actually, I don't remember off the top of my head. I do remember that the field of view of this is about 0.7 degrees left, right, and about a degree up and down. I'm trying to. I have a very simple worksheet going, which I can't seem to. There it is. Which I'm not really. Yeah, there it is. So my pixel scale is about 2.3 arc seconds per pixel, meaning that, all right, so for those of you who are not well familiar with angles and such, full moon is approximately 30 arc minutes in size, or half a degree. So if you took a degree on the sky and you cut it in half, that's how big the full moon is. Now, an arc minute is 1/60th of a degree. So take the full moon and split it into 30 equal width segments. That segment is 1 arc minute. Now take that segment and split that into 60 equally width segments, and each of those smaller segments is an arc second. So so I can measure, the best I can measure angular wise is about 2 arc seconds. If something is smaller than 2 arc seconds, then it's smaller than 1 pixel, and therefore I can't say anything about it. That is, at the very minimum, that is the error bar to my measurement, to my ability to measure. Now, there's more going to fall into the whole error analysis, but at the very least, I cannot measure the angular size of the sun to a precision less than 2.38. I agree with you in that portrait mode sucks. And the thing is, it's like that because it's an app on the phone and you can't landscape it. If you rotate the phone, you're looking at the phone like this, taking this image, and if you rotate it, it doesn't change. You can't landscape the damn thing. So I don't know, I'm just kind of stuck with it. But anyway, with the pixel scale, then I know that if my pixel scale is 2 arc seconds per pixel, and I know that the sun is roughly 800 pixels in size, then somebody with a bigger brain than mine can do the math. And what that comes out to, 2 times 800 is 1600 arc seconds. Divide that by 3600, and you get the size in degrees. So, Rocky, it makes you feel claustrophobic. I hear you. I always kind of want to take it and stretch and be like, what else am I not seeing? So it says, Stephanie asks or comments, sounds like pixel scale is all relative to already accepted values. Pixel scale is relative to your optical system, your camera and telescope. Sorry, Clive, I just saw your should be in radians. Yeah. Oh, pi sucks. Tau, ride and die. I'm all about the Tau, baby. Anyway, so pixel scale is relative based on your optical system. Some are going to be, if you have a very high angular resolution, then your pixel scale is going to be finer. It's going to be, 2 arc seconds per pixel. If your optical system is more coarse or more rough, then your pixel scale may degrade down to 1 arc minute per pixel, meaning that you really don't have very much resolution whatsoever. but it's not going to change what the physical size of the objects are. So again, because I want to compare apples to apples, here's the sun. You know, this is, I can measure this as with the same camera. Obviously, you can't measure the pixel scale using another optical system and then apply it to other images that were taken with a different optical system. But I can measure this, and you know, it's 800. I know, or roughly 800 pixels. I know each pixel corresponds to 2 arc minutes or 2.3 arc minutes. You run through the math, and I can figure out what the angular size of this is in degrees or radians if you want to be really rad. See what you did there, Al. I see that. Don't think I didn't see that. So yeah, you can measure it in that size. And again, if you do this over the course of many, many days, what hopefully I will be able to demonstrate, the expectation, my hypothesis is that the angular size will change as the distance to the sun changes over time. Now, now here is, with that, something immediately drops out. To quote many a physics textbook, it can be easily shown that the ratio of, how do I want to put this? I'm so worried about the physics book joke that I kind of forgot the rest of it. If you know the angular size of the sun, it can easily be shown that the angular size of the sun is simply the ratio between the linear size of the sun and its distance. Basically, tangent of that angle, that angular size angle, is equal to diameter over distance. Now, I have the angles. I have directly measured the angular size. So what that does is it now sets that ratio. It sets the ratio of size to distance. Therefore, if I were to assume a size about 6.69 times 10 to the 10th kilometers-ish? I don't know. I don't keep these things in my head. If I assume a linear size of the sun, really, really big, I can then, using the angular distance or angular size, determine the distance. I can then, if I have data from all over the year, and yeah, I am excited about this. This is what I geek out about this shit. I can by taking observations once every so often days, I can literally map out the motion of the Earth around the sun. I don't know about anyone else. That's fucking awesome. That you can do this. So, all right, calming down. So you make that assumption. Yes, Stephanie, I'm getting to that. You make that assumption. You say, all right, it is of this certain distance, of this certain size. You can then, if the statement would be, if the sun is in fact this diameter, then it must be this far away in order for me to have measured an angular size of of whatever 1600 divided by whatever I just said. Basically 800 pixels multiplied by 2, 1600 divided by 3600, that gets into degrees. If you want radians, then you have to deal with pi somewhere in there, yada yada. You measure a angular size. So given a distance, you can get a distance. Given a linear size of the sun, you can get a distance, or the opposite you can do if you wanted to do that. But where it comes to science skepticism, where this comes down to, and Angular size is not necessarily actual size. I don't know what you mean by actual size. Now, if you mean actual size by a size that is given in units of, say, meters, miles, kilometers, furlongs, that sort of thing, yeah, you're right. It's not. But it is part of it, as I was just talking about. With that angle, you can get the linear size, as I put it, a size in kilometers across the surface, if you know the distance. But like I said, when it comes down to flat Earth or science skepticism, at the very least, what this tells you is that ratio has to be constant. So if you tell me that the sun is only 3,000 kilometers above my head, then I can tell you, given these observations, just how big it is. I can even measure this in sheep units if you want to go that route. So this is, I think, useful for those of you, for those out there who are of the flat Earth persuasion. You know, you are constantly getting asked by us globies, howdy Judy. I'm showing off the toy that my patrons helped me buy. My little sea star here. Yay. This is an image. If you, I don't know when you showed up, Judy, but this is an image of the sun that I took with it. So for flat earthers out there, if you are wanting to know, we're constantly asking you, how far away is the sun? Or how big is the sun? Things of that nature. Well, at the very least now, you can, with these measurements, you can show that it has to be of a certain size to distance ratio. So if it is 3,000 kilometers away, then the size has to be of 100 kilometers in size or something like that. And from there, you can start to answer questions of like, what must the sun be composed of if you have a 100-kilometer sphere or disk that is creating a measurable brightness on the Earth? This is the type of thing that gets to science, is that ratios are relative only in the sense that if you want absolute values, you need to know one of the two values absolutely from an independent check. Crap. Nice. I often think about gravity in that when I hear that quotation. But that's what I'm talking about here, is that this is the beginning of, in my opinion, this is the beginnings of science, is that you see a phenomenon, you see that the sun is in the sky every day, and then you ask questions. Does the sun's size change over time? Now, if I were to do this rigorously, what I would do is, to answer that question, I would measure the sun at the same altitude that every day. That way, the atmosphere, any sort of contribution to atmospheric refraction is mitigated. That is something that I'm going to have to eventually take into account, because essentially I'm doing this whenever I have the free time to actually take this little one out and actually take these observations. My observations now have ranged from like noon to 4 in the afternoon. So much different heights or altitudes. So I'm looking through different strength or different amounts of atmosphere, which is going to affect the size of things. So I'm going to have to take that into account later on, and I have to think about how to do that appropriately. But this is how science is done, is you ask a question. does the size of the sun change as a function of time? You take measurements and you figure out whether or not that the answer to that question is yes or no. If that question is yes, then you can ask the question, what is the relationship between the change in size to distance? The experiment that I've laid out is I'm going to take these observations over the course of at least a year, and I'm going to look at the profile of the sun size with distance, the sun's linear or angular size as a function of the year. Then you can start asking questions like why? Why is it doing this? These observations, these are the facts that we deal with. These are the facts that we deal with in science. These are the things that we hang our hats on, that these are effectively indisputable within the error bars. And it's from these facts that we can create theories, or rather other hypotheses, to explain physical phenomenon. That is how we test whether or not a hypothesis is correct, whether or not the facts that we observe are in line with the hypotheses that we've made. So yeah, that is essentially the experiment that I want to do, and I'm going to try to milk this out. Oh, other one. That's right. The other thing is, see these spots? I don't know if I haven't fully downloaded everything. Again, I really wanted to have all of this downloaded and make it into a nice, pretty presentation, but yeah, I'm busier than a one-legged man in an ass-kicking competition. Let's see here. Yeah, I don't think I have. Maybe this one. Yeah, that'll work. So this was taken on the 14th. Oh, check out those beauties. Oh, yeah. Can't make this stuff up. So you have this grouping of sunspots down here. And then you have this large heebie-jeeba up here. Right? Keep those in mind. Keep the positions of those in mind. And then we look at one. Take it on the 17th. I think. I thought it was more dramatic than this, but what I'm hoping to be able to show you is that the sunspots move. Is that these spots are now significantly more to the lower right than they were before. This spot is actually moved just a little bit down to the lower right. And effectively, what you can do is by looking at the sun over the span of multiple days with what we call a cadence of one day at least, meaning that the span between observations is 24 hours or thereabouts, is you can watch the sun rotate. These sunspots are effectively localized or effectively stationary with respect to the surface around them, meaning they don't swim around. They basically hang out in the same place. And so when you see them move, that means this whole surface of the sun is rotating. So we can come up with these observations, we can come up with a fairly precise measurement of the rotation of the sun. We can determine how fast something is spinning that is purportedly at 149 million kilometers away. Blows my mind. I don't know about you all, but I'm really that amazes the hell out of me. Not only that, there's more. Is that the sun is not a solid body rotator. It's not like a basketball or this colorful stressy ball. You know, a solid body rotator means, like the Earth, is that once that the angular velocity of anywhere on the sphere is the same. Another way of putting it is that the period of rotation for any spot on the same is a day, or is the same. One day is one day wherever you are on the Earth. It's 24 hours, no matter where you are on the Earth. But a differential rotator, which the sun is, or has been observed to be, is that the rotation of the gas at the equator is about 27 days. It takes 27 days for the gas going around the equator of the sun to go around once. But as you get closer to the pole, that period gets longer, to the point that you're near the poles, the day on the sun, the period of rotation for the sun at that surface is about 30 days. So the sun literally wraps itself around itself. And with the sunspots, if you can get enough of these spots and you can figure out what the orientation of the axis, the rotation axis is to your line of sight, then not only can you map the rotation as a whole, but you might be able to even tease out differential rotation. Actually illustrate that the sun does not rotate as a solid body, but actually rotates faster at its equator than it does at the sun. But so yeah, and that's like, you need a lot of data to do that. And this isn't even one of my best ones. But yeah, Howdy Horizons View. So that's what I'm hoping to be able to do with this, and that's really what I want to share with the stream, was that I have this new beautiful instrument. And no, I don't sleep with it. Although, look at these curves. Would you blame me? Anyway, so I'm going to take all this data and I'm going to make it publicly available. Or you can, if you want to help me with this, because it's not going to be clear. It's not going to be, obviously it's not going to be clear all the time. My schedule as such is not going to be that I could potentially get out to where I can use this. So there's going to be gaps in my data. So if someone else also has a solar telescope that they can, want to be a part of this project, I think this would be amazing. I would love to see it. UK Pie, why do you not see the sun in Scotland? I'm fine. It's too drunk. Sorry, I'm trying to make a stereotypical Scottish joke about you guys are all alcoholics, but I think it's clouds. See, the atmosphere is nice. The atmosphere is wonderful, I guess, because it keeps us alive and stuff. But I gotta say, as an astronomer, the atmosphere kind of sucks. I could really do without it, because it kind of clouds over stuff, does other things. So yeah, that's what I want to do with it. And I think this is it's an accessible project. Like I said, I'm going to be fully transparent. I'll put my data up on my website, hopefully this weekend, and I'll try to do that weekly. And I will post the spreadsheet that I have updated on my website every week. At least that's the hope going forward. My website, for those of you who are not aware, is profparksphd.net. I think that's it. Yes. That website is up. It's really, really kind of sparse at the moment, but I'm hoping to be able to make it more of a clearinghouse of astronomical resources and things that I do. So, but before I go, because like I said, I'm burning daylight, as they say, because I've got other things later tonight that I need to do. So I want to get out there and actually take today's image. But there's a couple things that I want to talk about. Before I get into that, let's just have a little bit of fun. Hey, all right. So, 42 Deep Thought, monthly sun and earth videos. So if you have not subbed to Mr. 42 or Mr. 42 at Deep Thought, please do so. Very, very cool. Let's see here. I don't think I have any embarrassing photos of myself on my Google Drive, other than maybe that one. This is what the Unistellar looks like. So yes, it's definitely a directed energy weapon. And yes, when I pulled this out of the box, I did hold it up and go pew pew because it looks like a gun. Because yeah. Anyway, so when it comes to last night, was the first good night that I've had the time and resource to look at night sky objects with the Sea Star. And like I said, this is about a 10-minute observation of the whirlpool that I was able to take. Again, this is you set it up, you shoot it, and then you just wait there in the cold and let it do its thing. And really, this display, I don't know how it's coming out on the inner tubes, but there's a lot more detail and color in the actual image that I'm looking at on my laptop than it is here. Like there's some nice browns in there, like right in here. I tried to take an image of the pinwheel, which you can kind of see as another spiral galaxy. It's called the pinwheel because, well, it looks like a pinwheel, but it really didn't come out well. I don't know if this is an aperture problem or what. But so over the last couple of nights, I've been using both the Sea Star and the EV scope, and I kind of have a winner and a loser at the end of the night. In the first night, it was definitely Sea Star. Like it was easy to use, had no problems with it, and the images were just fantastic, particularly images of the moon. But last night, when I actually figured out how to focus it, the EV scope kind of took my breath away. Here's an image of the moon through the UV Unistellar, and yes, you can get rid of this annoying border. I have set it so that it will download both these little advertising images and ones that are not so advertising, that are just the image itself. And so you can see the kind of the detail. I can't seem to zoom in any further on Google, but you can see that. Zoom around. There's also there's interesting projects that I can do with moon images. I haven't really sat down to think about how I want to approach that, but you can do the same kind of thing, is that I can take images of the moon and I can determine the size, and I can do the same thing with the moon that I could do with the Earth or with the sun, is that I can see whether or not the size of the moon changes as a function of time, and not just obviously phase, but the size, the like up down size of it. Also, I can if I piece these together, I can actually show the libration of the moon's surface, in the fact that the moon does wobble. The portion of the moon that you can see changes, or the face of the moon that you can see actually does change with time. In that, we think of the moon as a synchronous rotator, meaning that the same face is always pointed towards you every night. Well, that's true to first order, but because of tidal forces, it's wobbling. It does this kind of thing, so that you can actually see a little bit more of the moon at certain times than you can at other times. So I think the number is we can see about, if you wait long enough, you can see somewhere in the neighborhood of 55 to 60% of the moon's visible, 55 to 60% of the moon's actual surface, because of this phenomenon known as libration, libration. And so, you can, if you take enough videos, I've seen this done, you've taken enough of them, you not only get to see the lovely change of the phase, but you can make a video of the moon dancing in the night sky. It's very cool. So I might do that as well. But there's the moon, but like libations, not quite the same thing as libations, but I do enjoy the occasional libation myself. I've got a few in my fridge, which is now over there. Don't tell anybody. No, I don't keep beer on the premises. Let's see. But the ones, oh man, I didn't download them? Oh, that sucks. I had to have downloaded them. Oh, yeah. There they are. All right. One object that I'd never even heard of was this one, which the pointing is actually slightly off. This is known as the Running Man Nebula. The actual really nice part of the Running Man Nebula is actually off to the right. I found when I actually Googled this later on. But I saw this and I was like, wow, look at this nebulosity. What's cool about this is a 5-minute exposure. Let me show you what it would look like when you first took a look at it. That is, if you were to stick an eyepiece onto this scope, onto the EV scope, and look through it, that is what you would see because of the light pollution. Because the sky is so bright, that nebulosity, that pretty stuff, is gone. But because of the way the telescope is designed, it will take an image, it will then save that image, it will then take another image that's around 10, 20, you can set it between 10 to 30 seconds. It will take another 10-second image, it will overlay it on the first one, and it will add. And it will continue to do that, and over time, you can change this into, well, there's 3 minutes. And then and then there's 5 minutes. So you can, so this is what we're talking about in terms of, no, in fact, it is not a debris field. This was a stellar nursery. This is where stars were born, and now all the star formation is done, and all the leftover gas is being slowly blown out of the system. So it is a debris field-ish if you consider that gas that did not go into stars as being debris. But that's not my fave. My fave is the favoriteest thing is, there she is. Oh, and that just does not do it justice. This is the Orion Nebula. Talking about star formation regions, this is the Orion Nebula. This is it's actually a minute and a half. I don't know why I didn't take a deeper exposure. Here's the full image. And you know what? It does still need to be collimated. This can get better because there's something about I won't get into the weeds about it, but the EV scope does still need a little bit more tweaking in order to get the images just right. Because you can see here that these stars are a bit oblate. They're a bit kind of oblong. If you compare them to the C star image field, these stars are pinpoints. They're little pinpricks. The UV scope, the aperture is larger, so it gets more light as a function of time. So it will be able to see fainter objects better, which is one of the reasons why, and the way that it adds things together, you get a darker background than what you're seeing here, but all of that can be kind of fixed in post-processing, fixed in post, as it were. But yeah, I'm going to have these up on my website as well, or on my website as well. I'm going to have a gallery of these things, but this is a minute and a half, and you can see, oh yeah, and again, in comparison to what you folks are probably seeing, in comparison to what I'm seeing on my monitor, is, pun intended, night and day. The structure that you see in here, basically, we refer to this as the bat wing, is that you have this emission coming off one side and the other. This is part of a much larger, what we call cloud complex, or cloud of molecular hydrogen and other stuff, and that is the building blocks of stars, of planets, and so forth. And these stars that are really bright in the center, this is not one big star. This is actually 4 stars that are so close together the light has bleeded out onto it. Those were some of the first stars formed in this cloud, and it is that light which is illuminating this gas, which is on, in some cases, a light year or so away from it. So that again, there you can illustrates just how empty space is. That light from a star can travel a light year without being changed or redirected or what have you overly much, and hit gas that's a light year away and cause it to light up, give its energy over to it, cause it to fluoresce, very much like a fluorescent light bulb. Here you can kind of see, again, I really wish, I can zoom more. There's nebulosity around here. Again, I really do need to work on the collimation of this thing. But there's a lot more detail. Again, it's amazing. And I really, it's a shame. Like I said, I'm going to put these up on my website. Hopefully those images will do it better justice than what you're seeing here. But when I saw this, I was nearly fell out of my seat. It was amazing. Because what I'm used to for astrophotography is doing it sort of the quote unquote old-fashioned way. The way that we do it here with the 32-inch is that we take images through filters. So we take an image only in the blue light, we take an image only in the green light, and an image only in the red light, and then we have to stitch those together or stack them on top of each other in order to get a true color, 3-color image. Getting the color balance right is such a pain in the ass. It is almost black magic. Like, it is really, really hard to do. Trying to think of, this is the Rosette Nebula, which is also an emission nebula as well. But after 5 minutes, I couldn't even see I can kind of see something might be there, but I think the Rosette Nebula is too big. Its angular size is too large for the field of view of the unistellar. Unlike the C star, the unistellar has more of a square field of view, and it's roughly about 0.7 by 0.7 degrees. So with the C star, you get a much longer field of view this way. Granted, you can crop it to make it look square, if that's what you think, or you can crop it to make it look landscape. However you want to do it. But the field of view of the C star is a little bigger, so I'm hoping to be able to see larger extended nebulae with it. The trade-off is that larger extended nebulae also tend to be fainter. And since the C star is smaller in aperture, I'm going to have to, it's going to be very, very long exposure. So it's this review process is going to take a while because I really want to do a lot of different trials with this sort of stuff. And yeah. All right. So that all being said, I do want to say that, you know, just because I'm a scientist doesn't mean that I'm not a dumbass. So we got this eclipse thing coming up. This eclipse on the 8th of April. Total solar eclipse for a certain portion of the population, running from Texas all the way up to about Maine, down into Mexico and up into Newfoundland for you Canadians. New Brunswick, Newfoundland, somewhere in there. And then the rest of the North America is going to see a partial solar eclipse to one form or another. Well, if you are going to watch the eclipse, you're going to look at the sun directly, you need a pair of these. Ultra stylish eclipse goggles or eclipse glasses. Your over-the-counter ones are going to be made out of paper, and they're going to have a film that is a neutral density filter. It blocks 99.98% of all light passing through it. That means the only thing that you can see is the sun. Like, I can't see you at all with these on. Now, so these are the safest way to observe the sun without magnification. That last part is really key, without magnification, because if you were to, like I did, have these on and then look at a sun through an eyepiece, through a telescope, 4-inch. So this is not a big telescope. This is a 4-inch telescope. What will happen is that the sun will literally burn a hole through your glasses. There we go. Nice little hole. Burnt or put there by the sun, and that light that burned through this plastic went directly in my eye. Thankfully, I am not blinded, at least not that I can tell. But so mostly it was my ego that took a hit. But yeah, don't do that. If you're wearing these glasses and you think, hey, sun's pretty small, let me grab my binoculars and stick them up to my face and look at it that way. I mean, I'm shielded, right? Don't do that. Bad people. Do not use these and look through anything magnified, because if you do, it will burn a hole through that. And it didn't take long. It took less than a second for the sun, through magnification, to burn a hole through this plastic and then into my eye. So, safety tape, Egon. Only unmagnified can you use these to look at the sun. If you were going to look at the sun using any kind of telescope, which if you're in George Mason, in the Fairfax area, please come on down. We're going to have some telescopes set up. They are 8-inch telescopes. They are sizable, so you'll have a nice view of the sun, but they are properly covered. They are properly filtered. They have these nice glass filters, so the sun comes in unmagnified, gets filtered, and then magnified to the eyepiece. Unlike what I did, which was to magnify the sun's light and then try to filter it, which was no bueno. So yeah. Welding glass. Okay. Thing is, and you know, yours probably, obviously it worked, but not all welding glass is the same, as you probably know. Some welding glass basically blocks more light than others. There is I don't remember what it is, but you want to, if you're going to, for those of you out there who are not Stephanie or her husband, if you were thinking of using welding glass as a replacement for this, then you need to look into the rating of that welding glass to make sure that it is sun appropriate. Some welding glasses can be used like this, others not so much. So yeah. All right. Well, that's all I got for today. If you are interested in this project and you have questions, then feel free to, where is it? No? Yes. There. Feel free to email me at parksj762@gmail.com. If you have any questions at all of anything, and really I do mean anything, if you want me to answer any questions that you have about anything, send them to me in email and I will answer them. I can't guarantee they will be correct answers. I can assure you that my astronomy related answers are going to be more correct than, say, hair care questions, like how to probably take care of one's hair. Probably not going to get as an accurate answer as if you ask me how long does a star live. But technically, the offer is open. If you have any questions, email me, ask me, and I will get them back to you. If you want to take part in this project of looking at the sun, like I said, email me, let me know, and we can work something out. So yeah. Thank you all for being here. Again, thank you for my patrons and channel support. That allowed me to purchase this. That support has also allowed me to purchase a planetary camera for the telescope, which will be used tonight during a Smithsonian sponsored event. We have a speaker that's going to be talking about Uranus. I'm not even going to say the other name because my inner 5-year-old can't handle it. He's going to be talking about Uranus, and unfortunately, I don't think Uranus will be up in the sky, but we're going to be using the planetary camera to look at Jupiter. And so because of channel support, I was able to purchase that for the observatory. So thank you so much again for all of that. But yeah, I am Professor Parks, PhD. I make content on astronomy, science skepticism, and mental health. If you like that sort of thing, please consider subbing. Sub, share, sub, share, and subscribe, or whatever. I can't remember the catchy little phrase that I use. Like, share, and sub, and share. Whatever. You know what I'm talking about. Hit that like button. Sub to the channel. Share this video with your loved ones, or if you hate this video, with people you don't like. Just share the video. And hit that bell for notifications, because I am a chaotic son of a bitch, and I do not post regularly. This is an off one for me. I actually advertised this yesterday, and I actually managed to start-ish on time. I had to push it back 15 minutes because I had to eat, but it's very rare for me to do that. Usually it's spur of the moment. So if you want to be notified in any way that these things are going to happen, hit that bell for notifications. And thank you all for coming, for being here. Maya, good to see you first time around. Horizontal view, I don't know if I've seen you around. Mr. 42, I haven't seen you here for a while, but thank you for dropping by. And for the rest of you, send it to Witsit. Nice. Yes, if you want to share my videos with Witsit, please do. With that, I hope you all have a beautiful day. And I'm going to play my outdated outro. Peace out and clear skies.